we present ReLMoGen, leveraging motion generation in reinforcement learning for mobile manipulation. Many real-world mobile manipulation tasks can be naturally segmented into a sequence of base and arm subgoals. For example, the door opening task can be segmented into a few base subgoals for the robot to approach the door and an arm subgoal to push the door open. These subgoals usually correspond to spatial points of interest in the environment, such as doors, chairs, cabinets, and waypoints through narrow passages. Classical motion generation algorithms have been widely shown to be good at generating and executing collision-free motion trajectories to reach these points of interest mentioned before. But they usually don't scale very well with larger search space with partial observability. On the other hand, tremendous progress has been made in reinforcement learning on solving visual motor control tasks. These algorithms are good at solving where to move to achieve a certain task given high-dimensional observation. However, they suffer from poor sample efficiency because RL with low-level joint motor control usually spends a lot of time exploring free space and obtaining little reward signal. In this work, we explore how to combine the best of both worlds. We propose ReLMoGen, a framework that leverages a motion generator in an RL loop. We lift the action space of the original problem from joint commands to subgoals. To put things side by side, in classical reinforcement learning with low-level action space, the agent outputs joint motor controls and receives observations and rewards from the environment. In our method, we lift the action space to motion generation subgoals. Instead of low-level actions, the agent outputs base or arm subgoals, and a motion generator plans and executes a sequence of low-level actions to accomplish these subgoals. Our subgoal generation policy, parameterized by a neural network, takes in RGBD images, one-beam LiDAR scans, and relevant task information as observation, and outputs base or arm subgoals as the new lifted action space. We stress test our method on a wide variety of 7 robotics tasks, including navigation, stationary arm control, interactive navigation, and mobile manipulation. Here, we show the reward curve during training. Our methods are indicated in red and green. They're able to consistently outperform baselines in all tasks and achieve higher task completion given the same number of training episodes. In the next few slides, we will showcase our best performing policies for all the tasks mentioned before. In the first task, the robot needs to travel from point A to point B without collision. Our solution is able to go through narrow passages without collision thanks to the motion generator. The red marker on the floor indicates a base subgoal as a desired base pose. In the second task, the robot needs to touch a point represented as a red circle on the table. Our solution sets the goal directly on the target and completes the task in one motion generation step. The yellow ball indicates an arm subgoal as a desired end effector position, and the red arrow indicates a desired pushing action from that position. The pushing action is not needed in this particular task, but will become useful in the next few tasks. The first 2 tasks allow us to see the strength of ReLMoGen in easy navigation or stationary arm control domains, although the largest benefits are in the more complex mobile manipulation tasks like the ones presented in the following. Next, we have 3 interactive navigation tasks. In the first task, the robot needs to push the door open with the gripper and go into a closed room. Our solution first travels to the door front, makes a few pushes, and then enter the room. In the second task, the robot needs to open the door by pressing a button. This is a task that requires high precision, and our solution is able to press the button very accurately. In the third task, the robot needs to push away an obstacle to clear the path. Only the red obstacle is movable, and the locations of the obstacles are randomly shuffled across episodes. Our solution is able to use the RGB information to make the right decision and push the right obstacle. Finally, we present two mobile manipulation tasks. In the first task, the robot needs to arrange a messy kitchen and close as many cabinets and drawers as possible. Our method is able to produce close to optimal interleaving sequence of base and arm motion and close multiple cabinets and drawers within the time budget. In the second task, the robot needs to tuck the chairs under the table. Our solution consistently navigates to a location behind the chair and pushes the back of the chair. We can also train the policy in one environment and then fine-tune on another environment. This is much faster than training from scratch. Here, we show a learned policy that is fine-tuned on another environment for push door navigation task. Here's another fine-tuning result on a novel environment for interactive obstacle navigation task. Our method is able to explore better and covers a larger space than baselines at the beginning of the training. Our method is also very highly interpretable. The learned subgoals are semantically meaningful and indicated useful interactions. For more detailed analysis, please refer to our paper. To summarize, we propose ReLMoGen, a framework that combines the strength of RL and motion generations. We show that our method is general because it not only works with two different RL algorithms and network structures, but also solves a wide range of long horizon tasks in navigation, stationary arm control, interactive navigation, and mobile manipulation. It works with different motion planners and has a great potential to transfer to real robots. We also plan to extend our framework to other action primitives, such as pulling and turning, that can be instantiated by our RL policy in the future. Thank you for your attention.